All right, so today we're going to talk about solubility. Solubility is like when you take some salt and put it in water and stir it up, the salt appears to just disappear. Well, what's really going on there is that you have water molecules, and the important thing to know about water molecules is that they are polar. Now, we'll get into all the polarity aspects of it next unit, but for right now, just note that water is an asymmetrical molecule that has one side of it that is more negative and one side of it that is more positive over here. So it's got a positive side on one side and a negative side on the other, so it kind of makes it into a tiny little magnet. And that matters because remember, if you've got a negative side and a positive side on a water molecule, and that water molecule goes to interact with ionic compounds, remember that ionic compounds also have positive and negatives in them as well. So now what you have is you have a little bit of a tug of war going on. The positives to negatives are going to be attracted to each other here in the ionic compound, but the positives and negatives in water are going to be attracted to the ions as well. So the negative is going to be attracted to the positives, and the positives are going to be attracted to the negatives here. And so you could have a situation where the ions are actually more attracted to the water than they are to each other. And if that's the case, then those ionic crystals get ripped apart by the water molecules, and now what you have is you have, for instance, a negative ion here that is surrounded by a bunch of water molecules, all with their positive sides pointed at it. So positive, 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 and positive, all towards that negative that's there, right? And that attraction is more than the attraction of the positive and negative toward the crystal itself, which is why it's been ripped apart. Now the same thing is true over here, except over here you've got a positive ion, and you'll notice that the negative side of all of these guys are pointing at the ion. So what you end up with are what are called aqueous ions, and the term aqueous is oftentimes seen as AQ, right? So if you see something like Na plus 1 AQ, what it means is that it's a sodium ion that has been ripped out of the crystal. So again, here's your crystal, and the sodium ion has been ripped out of that crystal and is now surrounded by water molecules and is free to roam around in the beaker there. If you were to see this for the chloride, it would be the same thing, except that it would be a Cl negative 1 with an AQ next to it, because the chloride ion has been ripped out. And again, you'll notice that the positive side of the water molecules is all pointed toward the negative ion that's here. And here, the negative side of all of the water molecules are pointed towards the positive side that is there, right? So aqueous ions are when an ionic crystal is ripped apart by the water molecules. Now, so does that mean that all ionic compounds are going to be ripped apart by the water? Well, it turns out no, because remember, there's two factors. There's the factor of the ions' attractions towards each other, and then there's the factor of the ions' attraction towards the water. If the ions' attraction for each other is more than the ions' attraction for the water, then it'll stay together. But if the water's attraction is more than the attraction of the ions for each other, then it will rip apart. Well, how are we supposed to know? Well, let's take a look at some examples. Now, I'm not going to go through every single one of these, but there are 12 different examples here of ionic substances. And when you look at these different ionic substances, they all kind of look very similar to each other. But if we were to run an experiment with each of these guys and take a little bit of each of these substances and put them in the bottom of the test tube, and then add a little bit of water to it, and then put a stopper on and shake them up, here is the results that we would get. Now, there's a couple of different things here. First of all, you'll notice that some of them are cloudy. So let's take a look here at number 3. Number 3 looks cloudy. Now, number 2 is yellow, but it's not cloudy. It's still clear, right? So I'm not talking about the color here. I don't care about the color. I care about whether or not you can see through it or not. The cloudy one here, number 3, is of interest to me. Number 6, also cloudy here. So this one here, also cloudy. And then here's numbers 10 and 11 and 12, also cloudy for those guys. So what's up with those as compared to the ones that are clear? Well, if we take a look at this and now break them into two different groups, and those two different groups, you'll notice this group here are all of the ones that are clear, and the ones that are here are all of the ones that are cloudy, right? We can see that if it's cloudy, we can make a reasonable assumption that they are insoluble, meaning that whatever was going on in the crystal, that crystal was a strong crystal. If the crystal is strong, then this crystal was not ripped apart by the water molecules, and it stayed together. And if it stayed together, then the light can't really get through or around those ions, which is why it is cloudy. So the ones that are the strong crystals here, these guys here are all strong crystals, which is why they did not dissolve. They're insoluble or cloudy. They stayed together. Everything else here was clear. They're all soluble. So let's take a look at those. So here's number one. Notice in number one that when you put it in the water, it's obvious that the water was able to rip the crystal apart because that solution that you see here is a clear solution. It was not ripped apart, or it was ripped apart. Numbers 4 and 5, also clear. There's no cloudiness going on in numbers 4 and 5. Those must be weak substances. Numbers 7, 8, 9, also weak substances because, again, they are clear, right? Number 2, also a weak substance. It's yellow, sure, but it is a weak substance because you can still see through it. So all of the other ones here are clear. And with those ones that are being clear, those are all of the soluble ones. And the soluble ones are all of the substances that are weak. They will be able to be ripped apart. Now, what is the only determining factor between each of these different substances? Well, what's the only real difference between an ionic compound? It's their charge and their size. Well, size is tough to tell, but charge is pretty darn easy. Let's check out their charges. So if you check out their charges, here is number one. Number one is +2 and -1, +1 and -2, +2 and -1. And we go through the whole list here, right? There are all those. Now, why are those different than these here? Do you see differences between the two different charts here? Take a moment and see if you can't spot a difference. I'll give you a hint. There are charges that are here that are not present here. Do you see them? Pause it, take a look, and then unpause and come back. I'm going to assume that you paused and have come back. Did you notice that there are no ones down in the bottom one, but there are ones in the top one? Take a look. In the top one, I got a -1, +1, -1, +1, both positive and -1, +1, +1, -1 here. Every one of these guys has either a +1 or a -1 or both. But down here in this chart, there are no +1s. There is not a +1 and there is not a -1. No +1 or -1 in this list that is down here. So what does that tell you? The presence of a +1 or a -1 charge is most likely going to lead to the substance being soluble. Why? Because what is the weakest positive charge? +1. This is the weakest positive charge. What's the weakest negative charge? -1. That's the weakest negative charge. So generally speaking, if you've got a +1 charge or a -1 charge, you're probably going to be a weak crystal. And if you're a weak crystal, you're probably going to be soluble and therefore be ripped apart. Here are substances that don't have any weak charges. There's no plus ones and there's no minus ones in any of those substances. So because there's no weak positive or weak negative, only strong positive and strong negative, those substances are generally insoluble. Now, that is a general rule which gives you an idea of how these things are governed. And the general rule is that an ionic compound will probably be soluble if it's got a +1 or a -1 charge in it. Now, when I say that's a general rule, it's because there's lots of exceptions to this. Back in the day, you had to memorize this chart. And this chart told you that all of those were always soluble. All of those were always soluble. All of those were soluble unless it was with one of those. That was always soluble in spite of the fact that it was a -2, unless it was with one of these. So back in the day, the AP folks made you memorize this whole chart. Now they don't. They've gotten rid of a whole bunch of the memorize aspects of everything. So the only rule that they're going to ask you to know for the AP test is this one. These 4 ions. Sodium +1, potassium +1, ammonium +1, and nitrate -1. All of those substances are always soluble. That's the only ones that you have to remember. And all of those kind of go with our +1, -1 rule that's there. Now, if you get on the AP test and you apply the +1, -1 rule, they're not going to know what you're talking about. So don't bring that up. It's a general rule used as a general guideline to give you an idea of what's what. If they tell you on the AP test, here is a substance, and that substance is a +1 and a -1, but they tell you that it is insoluble, believe them, because there are those that exist. For example, silver chloride. Ag is a +1 and Cl is a -1. You would think that this substance would be insoluble. I'm sorry, you would think, I apologize, that this substance would be soluble because it should be weak. It's got a +1 and a -1 on it. And you would be wrong. This is an insoluble substance. It turns out that this one is strong. Why? It's an exception, and there's lots of exceptions there, which is why I keep saying that this +1, -1 rule is a general rule. It gives you a general idea of whether or not it's probably soluble or insoluble. So go with what they say on the AP test. If they say substance X is insoluble, believe them. If they say substance Y is soluble, believe them, all right? And the only ones that you have to know are these 4 here. These are always soluble.